Okay, so we're going to go through rate of change, and specifically we're going to start off with average rate of change. Okay. In order to calculate rate of change, we need usually at least 2 points on a graph. So our very first example, A. We have 2 coordinates which we're going to write out here so that we can use them to calculate the rate of change. This first coordinate is 200 and 400. And the second coordinate is 400 and we'll say 700, roughly in between there. Okay. Now, if rate of change is talking about the vertical distance over the horizontal distance. Okay. So we have to find the change in both of these. For our very first one here, do I have room beneath? I didn't quite leave room here. So we're going to be looking for I'm going to use a triangle to describe change. Okay. So the change in the y over the change in our x. Delta y, delta x is also known as. Okay, so that triangle there means change in y divided by the change in x. So in this case, our change in y, well, we're going to take our 2 y coordinates to help us figure them out. Yeah. So if we need to figure out the change of this, that would be 700 subtract the number 400. So let's say we're writing a little formula for it. We'll say the ROC, rate of change, or in this case, because we're doing average rate of change, and I'll talk about the difference after, is going to be equal to 700 subtract 400 divided by, and then we have to find the rate of change of our x values. Well, that's going to be taking 400, okay, and subtracting 400, subtracting 200. Okay. So we're looking for these rates of change. We're going to talk about which ones to use first and which ones to use second after. I'll relate it after to both of them. So we're going to end up with the number 300 on top and 200 on the bottom, which is equivalent of that what? Anyone know? 1.5. Now we have to talk about what our measurements were here, and I should have written that down. We're going to say this was cost over distance driven. So this was cost, so our price over a distance.
Oh, 1.5.
Yeah. So what it ends up being, if we divide this, we can still make this a fraction of 1.5 over 1. So the 1.5 was our y-axis, which was our cost. So our cost over our distance. And what that means is for every $1.5 we spend, we can go a distance, and we'll say it's in kilometers, a distance of 1 kilometer. Okay? This is very similar to slope, which you guys would have done in grade 9, where they talk about x1, y1, x2, and y2. Okay, and we did this earlier in the year when we were talking about correlation rates. Okay, this is the exact same idea. They just use different ways to describe it. Okay, and I know it looks a little messy what we've done here, but this is the general idea. So, question B. One way that will help me if I'm trying to figure out what type of slope I have, I can recreate a graph, or I can use just the 2 coordinates they've given me. So I'm going to scroll to the bottom to solve B. The coordinates they've given us for this question were 0 and 2,000. And the other coordinate was 4 and 1,400, I believe. Okay. So it looks like we'll call this our first and our second point. So if we were to do this the way we had done slope previously, this would be our x1 and our y1, x2 and our y2. Okay? If you guys remember slope, we have our y2 minus y1 divided by x2 minus x1. And those are identical to the change in y divided by the change in x. That's exactly how they're describing those 2 things. So we're going to plug our values in for this. Our y2 was 1,400, so 1,400. Subtract y1, which was 2,000. Divided by x2, which was 4, minus x1, which is 0. Okay? That is going to be equal to, what is 1400 minus 2000? Anyone know? Negative 600. And 4 subtract 0? 4. So, what am I going to get in the end? First of all, this is a negative divided by a positive, so my answer will be negative. And what will the value be? 150. Okay? But what are we talking about? And remember, when we break it down to one number, we could always rewrite it as a fraction over 1 to help us make sense of, to give it a unit value. So, our y-axis here was the flight height. So we're assuming this is a plane, and this is over time, we'll say in minutes. Okay? So the height of the plane, so it descends, so it's going down. Negative 150 is the height of the plane. Oh, let's spell that right. We'll say meters again. So let's say height in meters over time in minutes. Okay, so time in minutes. So how we would interpret this would be we're going down 150 meters for every 1 minute. That's the average rate of change of this plane. Okay, so average rate of change is pretty identical to calculating slope. It's not always the best way to describe a rate of change, though, because within an average rate of change, we could have different rates of change. Okay? Now, finally, I'm going to talk about one more. Here's question 3. I know this is getting a little disorganized here. We're going to turn this into a chart to help us make sense of it. Okay? This is speed in kilometers an hour in reference to reaction time in distance per meter. Okay? So I want to rewrite this, and I'll put it below in a chart. So I'll make a new line so it gets a little cleaner here. Now, assuming, what would be our independent and our dependent variable here? If we're talking about a car, maybe, someone driving a car, what do we think would be the independent variable, and what would be the dependent variable? That's right. Our speed would be the independent, and our reaction time would be dependent. So depending on how fast we go, it will draw a reference to how fast we can actually react. So speed. Speed is our x. Okay. And y is reaction distance. I'm just going to call it RD. Let's change that a little. So we have RD in this case. I'm going to write them back down, don't worry. Speed was going in terms of tens, so 0, 10, 20, 30, 40, and actually went up to 50. Okay. And reaction distances, I memorized them already, are 2, 4, 6, 8, 10. Oh, I forgot 8. 2, 4, 6, 8, and 10. Okay? So here's reaction distance. Now here, an average rate of change is referring to just specifically 2 points. Okay? So if I wanted to find an average rate of change from the start to the end, I would only need those 2 points. It wouldn't tell me the story of what's happening in between. Okay? What we're going to do here is we're going to find the rate of change of all of these. And this is very similar to first differences. In fact, it's identical. Something you guys would have done hopefully in grade 9. And what first differences are is we find the difference between all of the y values. Okay? So we take the second one and subtract from the first. Okay? So I take the value of 2, I subtract 0, I get a rate of change of 2. I then take the next value and subtract from the one above it. 4 subtract 2 gives us 2. 6 subtract 4 gives us what? What did the next pairing give us? And the last pairing? Okay, so our rate of change is what here? How would you describe this? Okay, it is a first difference. Linear is one way. It's constant is what we're really looking for. This is a constant rate of change. So if I had decided to find the average rate of change between the last taken coordinate and the first, that would actually be very true of a constant rate of change, okay? It would pretty much give us what we're looking for, the average rate of change here, okay? But let's say We have another question. We're going to do speed versus braking distance. We'll do the same thing. We'll set it up so that it's easier to do our first differences or our rate of change. We'll do speed and braking distance here. This is question D, yeah. So our speed was 0, 10, 20, 30, 40, and 50. Okay. Our braking distances were a little different. We had 0, 0.5, 2, 4.5, 8, and 12.5. Okay. So let's find the rate of change. In order to do rate of change, again, we assume speed is our independent and braking distance is our dependent. In order to do this type of first difference, our first check should actually be on the independent. We have to make sure that it is changing by a consistent amount. Otherwise, we can't really carry out this test. Now, are the speeds all measured by the same scale here? Don't do that. Okay? They're all changing by 10. Our distance, though, we're going to figure out what they're changing by. So we have our second number, subtract our first. That's right. Gives us 0.5. Then we take our number 2 and subtract our second value. So 2 subtract 0.5 gives us 1.5. Okay? 4.5 subtract 2 gives us 8 subtract 4.5. That's right. And 12 subtract 8. Okay. Now, our rate of change, what I really want you to notice is that it is constantly changing. And you're right, the rate of change seems to be increasing by the value of 1 every time. But what's important is we notice that this is a changing rate of change in another lesson. Okay. So for rates of change, we need to be able to describe them as consistent, changing. Where is it? That's what I'm... Okay. So we either have consistent rates of change, changing ones, or we have one that would be considered 0. What would, on a graph, a rate of change of 0 look like? Okay? Let's say I'm drawing a straight line. That'll be my hint to you. What will a rate of change of 0 be? 0. What would the line look like? Horizontal. This is a rate of change of 0. Okay. Our rate of change here, that's supposed to be an R and O and a C. Wow, that doesn't really work very well. Let's zoom in again. Our rate of change in that instance would be 0, which is, if you do not remember slope, the slope of this would be 0. What would the rate of change of something like this be? A vertical line. So say we do this one in green. Wouldn't be 1. What would the rate of change or the slope of this be? It's a very large number. So large, we really don't usually give it a value.
0.
This would be an infinite rate of change, okay? Because what's happening is at that same point, it's continuously going up, okay? So just keep those in mind. A horizontal line gives you a rate of change of 0, where a vertical line gives you an infinite rate of change. Okay? Obviously. Okay, so there's everything we went through today.
Then Mr.